Somewhere out past the numbers you can hold in your head, the primes go quiet. They arrive in little bursts, then fall into long silences, and nobody has ever found the rule that decides which comes next. A pair of twins, then a desert. Everyone who has looked closely says the same thing, that up close they look like scattered gravel, but stand far enough back and they thin out with a precision so exact that a 15-year-old boy, counting by candlelight, wrote the law down before anyone alive could prove it. So this is going to be a long one, and it is meant to be. There is nothing here you need to solve tonight, and nothing you have to remember in the morning. If you drift off somewhere in the 1850s and wake up in a common room in Princeton with the tea going cold, that is not a failure. That is roughly how the story went for the people who lived it. Let me start where every version of this starts, which is with the number line as an object you can actually picture. Imagine a long ruled tape stretching off into the dark, marked 1, 2, 3, 4, and so on forever, with a small brass lamp lighting only the section directly in front of you. Most of the numbers on that tape are made of other numbers. 12 is 6 2s or 4 3s or 2s and a 3. 15 comes apart into 3 and 5. 900 is a whole workshop of smaller pieces stacked together, but scattered along the tape are numbers that will not come apart at all. 2, 3, 5, 7, 11, 13. You can push on them as hard as you like, and they refuse to split into smaller whole pieces. Those are the primes, and they are the reason arithmetic has a flaw. There is a lovely word for them that goes back a long way in the literature, which is atoms. Not atoms in the modern physics sense of protons and electrons and the whole humming apparatus, but atoms in the older Greek sense, the sense the word actually carries, which is uncuttable, a thing you have reached the end of. And the moment you allow yourself to think of the primes that way, as the uncuttable pieces from which every other number is assembled, the whole subject changes character. Arithmetic stops being a set of procedures you were drilled in at a small wooden desk and becomes something closer to chemistry, with a periodic table you did not know existed. The reason that picture holds up is a statement so basic that it hides in plain sight for most of a lifetime. Every whole number above 1 can be built by multiplying primes together, and there is exactly one way to do it. Not roughly one way, exactly one, if you ignore the order you write the factors in. 60 is 2 times 2 times 3 times 5, and it will never be anything else. Not in this universe, not in any other, not on a chalkboard in a lecture hall in Vienna, and not on a clay tablet in Uruk. That statement is called the fundamental theorem of arithmetic, and the name is doing real work. Everything else in this story rests on top of it. Every number carries a unique fingerprint written in primes, and it carries it permanently. That result was first set down properly in Euclid's Elements, the great geometry text assembled in Alexandria around 300 years before the Common Era, in the city with the lighthouse and the harbour and the library that everyone still argues about. We know almost nothing about Euclid the man. We do not know where he was born or what he looked like or whether he was one person or a committee working under a shared name, which is one of those quiet historical facts that ought to bother us more than it does. What survives is the book. 13 volumes of propositions, each one built on the last, laid out with a patience that reads today like someone stacking stones very carefully in low light. And buried in that book, in the 9th volume, is a proof that I would put forward as the most beautiful short argument ever written down by a human being. It concerns a question that would occur to anyone who has stared at the number line long enough to notice the primes thinning out. Do they run out? Somewhere far along the tape, does the supply simply stop, so that past some enormous final prime every number can be broken into smaller pieces? Euclid's answer is no. And the way he gets there takes about 4 sentences. Suppose the primes did run out. Suppose you have them all, the complete list, every uncuttable number that exists, written out on a scroll on the table in front of you. Now multiply them all together, all of them, every one on the list, into a single gigantic number. Now gently, add 1. Consider what you are now holding. This new number cannot be divisible by any prime on your list, because dividing by any of them leaves you that stubborn remainder of 1, sitting there like a pebble in a shoe. So either this new number is itself prime, in which case it is a prime that was not on your complete list, or it is built from primes, in which case at least one of those building blocks was not on your list either. Either way, the list was not complete, and since the same argument works no matter which list you hand me, no list can ever be complete. The primes go on forever. There is something almost impolite about how efficient that is. 2,300 years, an entire civilization risen and fallen and risen again in different clothes, and nobody has improved on it, because there is nothing left to improve. It does not require algebra. It does not require calculus or set theory or any of the machinery that came later. You could explain it to a thoughtful child with a stick in wet sand, and the child would get it and would then be in possession of a permanent fact about infinity. But there is something Euclid's proof does not tell you, and that gap is where the rest of this story lives. He proved the primes never stop. What he did not do was tell you where they are, or hand you any way to inspect a number and say whether it is prime without checking, or say how many primes lie below any particular point on the tape, or predict the gap between one prime and the next. The proof guarantees an infinite supply and says nothing whatsoever about the distribution. It is a bit like being handed a certified guarantee that there are infinitely many islands in the ocean, with no map, no coordinates, and no indication of whether the next one is over the horizon or under your boat. For the practical business of actually finding them, the ancient world had one good tool, and it also came out of Alexandria. Eratosthenes was the librarian there, a generation or so after Euclid, and he was the sort of person who is slightly infuriating to read about. He measured the circumference of the earth using shadows in 2 Egyptian cities and a bit of trigonometry, and got remarkably close. He drew maps and worked on the calendar. His colleagues apparently nicknamed him Beta, the second letter, because he was reckoned second best at everything and first at nothing, which says more about his colleagues than about him. His method for finding primes is still taught, and it is still the thing you would reach for if someone handed you a grid of numbers and a pencil. Write out the numbers in rows on a sheet of paper. Circle 2. Then walk down the sheet, crossing out every multiple of 2 all the way to the end. Come back. The next number still standing is 3, so circle it and cross out every multiple of 3. Come back again. 5 survives, so circle it and cross out its multiples. Keep going, and the composites fall away in these long diagonal sweeps like rain across a window, and what is left uncrossed when you stop are the primes. It is a sieve in the literal sense, which is why it carries that name. You are not finding the primes at all. You are removing everything else and looking at what remains, and that is a subtle and rather melancholy point about this entire field, because it turns out that this remains more or less the situation. We do not have a formula that generates the primes. We have a sieve, and we have a great deal of very deep mathematics about what the sieve leaves behind, and the gap between those two things is where 2,000 years of frustration lives. Now here is where the real problem opens up, and I want to take it slowly because everything after this depends on feeling it rather than just hearing it. Spend a while with a table of primes, not a summary, an actual table, the sort of thing that used to be printed in the back of reference books in columns of small type. In the first 100 numbers there are 25 primes, which is a comfortable density, roughly 1 in 4. Between 100 and 200 there are 21. Between 100 and 1,000 and 1,100 there are 16. Climb higher and the columns start to look sparse, then thin, genuinely lonely. Out past 1,000,000 the primes are scattered like farmhouses on a plain at night. A light here, nothing for a long time. Then 2 lights close together. That thinning is not surprising once you think about why it happens. A large number has more potential divisors below it than a small number does. So it has more ways to be composite, more chances to be caught in the sieve. The surprise waiting in those columns is the manner of the thinning, because up close they are maddening. The gaps are irregular in a way that feels almost deliberate, almost like being teased. You get twin primes, pairs separated by only 2, like 11 and 13, or 101 and 103, and these keep turning up no matter how far out you go, at heights where you would swear the supply must have thinned past the point where such pairs are possible. Then, without warning, you hit a stretch of 100 consecutive numbers with not one prime among them, and it is easy to build such a stretch, and easy to build one 1,000,000 long if you feel like it. There is no rhythm. There is no visible rule. Generations of extremely serious people have stared at those columns looking for a pattern in the local behavior and have found precisely nothing. And yet, stand back far enough, stop asking where the next prime is, and start asking how many primes there are below some point, and an entirely different creature walks into the room. The count behaves. It is smooth, and it follows a curve so clean that you can predict it out to millions and be wrong by a handful. The primes are locally chaotic and globally obedient, and that combination is the deep strangeness at the center of this whole subject. It is the mathematical equivalent of a crowd, where you cannot predict what any one person will do, and yet the flow through the station at 8 in the morning is the same every day to within a few dozen people. Somebody was going to notice that. And the somebody who noticed it first was 15 years old, working alone, in a small German town, with a table of logarithms he had been given as a present. His name was Carl Friedrich Gauss, and in 1792 he was living in Brunswick, in what is now Lower Saxony, the son of a bricklayer and gardener who could not see the point of any of it. His mother could barely write. The family had no money and no expectation that a boy from that house would do anything but work with his hands. What saved him was that the Duke of Brunswick had been told about a child who did arithmetic the way other children breathe, and the Duke, to his eternal credit, paid for the boy's education without much fuss about it. Around that year, Gauss came into possession of a book of logarithm tables. The modern ear hears the phrase book of tables and imagines something dry. It was not dry. In 1792, a good table of logarithms was a serious piece of technology, the kind of object that navigators and astronomers depended on. Thousands of numbers computed by hand over years and printed in tiny columns on thin paper and bound into the back of the particular volume he had, as a supplement, was a list of the prime numbers. Most boys of 15 who were given such a thing would have used the logarithms and ignored the appendix. Gauss ignored the logarithms and went straight for the appendix, and having exhausted it, began extending it himself. Here is what he actually did, and it is among the most quietly astonishing work habits in the history of science. He divided the number line into blocks of 1,000, which he called chiliads, from the Greek word for 1,000. Then he counted the primes in each block, by hand, with a pen on paper, one block at a time. In the letter he wrote about it decades later, he described the practice as spending an idle quarter of an hour here and there counting a chiliad, which is the single most Gaussian sentence ever composed. Other people spend an idle quarter of an hour looking out of a window. This man spent it manually tallying prime numbers in the 400,000s, and he kept doing it on and off for most of his adult life until his private tables ran out past 3 million. Picture the physical reality of that. A wooden desk, a candle or an oil lamp, a stack of ruled white sheets, and a man working through a block of 1,000 integers checking each one for divisibility. It is monastic work. It is the arithmetic equivalent of copying out a manuscript by hand. And he was not doing it to publish, and not doing it because anyone had asked, and not doing it for a prize. He was doing it because he wanted to see the shape of something, and the only way to see it was to count. And what he saw was this. The primes in each block were dropping off, but not in a way that felt random. The count per 1,000 fell steadily, and the rate at which it fell tracked something he recognized, because he had a table of logarithms open on the same desk. Near a number, call it x, the primes were showing up with a density of roughly 1 over the natural logarithm of x. Let me unpack that gently, because it is the beating heart of everything that follows, and it deserves better than being tossed out as a formula. The natural logarithm is a way of asking how long something has been growing. If you picture a quantity that grows continuously, always increasing in proportion to how big it already is, the way a healthy population or a compounding account or a bacterial colony does, then the natural logarithm of a number tells you how much growing time it took to get there. It grows very slowly. The natural logarithm of 100 is about 4.5, of 1,000, about 7, of a million, about 14, of a billion, about 21. You are multiplying the input by 1,000 each time and the output creeps up by 7. So Gauss's observation says that around 100, roughly 1 in every 4 or 5 numbers is prime. Around a million, roughly 1 in 14. Around a billion, roughly 1 in 21. The primes are getting rarer, but at a pace so leisurely that it is almost tender. They never fall off a cliff. They just quietly become less common, forever, at exactly the rate the logarithm describes. And that immediately suggests the next move, which the teenager made without hesitating. If you know the density of primes at every point, you can add up the density to get the total count. That is what an integral is. Walk along the number line from 2 onward, and at each point deposit 1 over the natural logarithm of where you are standing, and keep a running total. That running total, that accumulated area under the curve of 1 over the logarithm, is called the logarithmic integral, and Gauss's conjecture was that the number of primes up to any point is closely approximated by it. He was 15. He had no proof and no theory of why it should be true. What he had was a table, a pen, a habit of counting, and an eye that saw through the noise to the curve underneath. And he was right, in a sense that took another 104 years to make Diehrebemente. Then he did the thing that makes historians of mathematics sit down heavily in a chair. He did not publish it. He never published it. Not in 1792, not in the great work of 1801 that made his reputation, not in the decades of celebrity that followed, not once in 60 years. The single most important conjecture about the distribution of prime numbers sat in his private papers while he built the rest of modern mathematics on top of it, and the world found out about it almost by accident, because an astronomer wrote him a letter. The astronomer was Johann Franz Encke, director of the Berlin Observatory, a former student, a man who has a comet and a gap in Saturn's rings named after him. Encke had been thinking about the frequency of primes and wrote to Gauss about it, the way you might mention a hobby to an old teacher. And on Christmas Eve of 1849 in Göttingen, an old man of 72 sat down to reply. That letter is one of the great documents in the history of number theory, and what is in it is not what you expect. Gauss tells Encke that his interest in the question goes back to 1792 or 93, after he acquired the Lambert supplement to the logarithm tables. He describes the chiliads, the idle quarter hours, the white sheets. He says that he soon recognized that behind all the fluctuations, the frequency of primes is on average inversely proportional to the logarithm. There is no boasting anywhere in it. The tone throughout is that of a man describing a garden he has kept for a very long time. Then he does something few people of his stature ever did, which is to show his working. On the second page of the letter, he lays out a comparison between his logarithmic integral and the actual counts from his tables, band by band, across the millions. The agreement is startling. In one stretch of 100,000 numbers, up near 2.6 and 2.7 million, the tables gave 6,765 actual primes. The logarithmic integral predicted about 6,761, 4 apart, out of nearly 7,000, in a region of the number line where no human being had any business predicting anything. A boy's guess from 57 years earlier was off by 4. That is a haunting level of agreement. That is the kind of agreement that tells you there is a law underneath, that the disorder you see among individual primes is surface texture on something rigid and structural, the way ripples on a pond are surface texture on a body of water that has a definite shape. Which raises the obvious question, and it is a question about a human being rather than about mathematics. Why did he not publish? There is no single answer, but there are pieces of one. Gauss's motto was a phrase meaning few, but ripe, and he meant it with a severity that frustrated his contemporaries and continues to frustrate people 2 centuries later. He did not consider a result finished until it was proven, polished, and stripped of the scaffolding that got him there. He compared himself to an architect who takes down the scaffolding before showing the building, which sounds elegant until you realize how much mathematics sat unpublished in his drawers, while other people spent their careers rediscovering it. Non-Euclidean geometry, aspects of complex analysis, elements of what became statistics. He had them, and he sat on them because they were not ripe, and the prime conjecture was, by his own standards, deeply unripe. He could not prove it. He could not even sketch a route to proving it. All he had was overwhelming numerical evidence, and numerical evidence was not a proof, and he was not a man who confused the two, so it went into a drawer and stayed there, and the world was left to catch up on its own. There is a second reason, quieter and more human, and you can feel it in the letter to Encke. He liked the problem. He kept coming back to those tables for decades, extending them, checking them, adding chiliads well into old age long after he had nothing left to prove to anyone. This was what he did when he wanted to be alone with something beautiful. Publishing would have turned a private pleasure into a public position, and my sense, reading the letter, is that he simply preferred to keep it. But while he kept it, someone else was working the same ground and had no such reservations, and that man got to print first. Adrien Marie Legendre was working in Paris, and he was in almost every way Gauss's opposite. Older by 25 years. Sociable where Gauss was private, willing to publish an idea while it was still warm, and unbothered by the possibility of being partly wrong in public. In 1798, in a book called An Essay on the Theory of Numbers, Legendre put forward his own approximation for the count of primes. He refined it in a second edition in 1808, and the refined version is the one that got quoted for the next 50 years. It said that the number of primes up to a given point is roughly that number divided by the quantity you get when you take its natural logarithm and subtract 1.08366. That constant is the interesting part. 1.08366. Where does a number like that come from? It came from the tables. Legendre had the same kind of prime tables Gauss did, and he fitted his formula to them, adjusting the constant until the curve lay down meekly on the data. It is honest empirical work of exactly the sort that engineers and astronomers did constantly in that era, and by the standards of 1808 it was a genuine contribution. For numbers in the range anyone could actually check, Legendre's formula was excellent, better than the raw logarithmic integral in some stretches. Gauss saw it, and in that same Christmas Eve letter to Encke he gives his verdict, and the verdict is polite and devastating. He acknowledges that Legendre's formula produces a smaller error over the range of the available tables. He does not dispute the arithmetic. Then he points out that the rate at which Legendre's error grows is much greater than the rate at which his own error grows, and that the constant 1.08366 is not a constant of nature at all. It is a curve-fitting parameter. It fits the tables of 1808 because those tables stop where they stop. Push out further, Gauss says, and that constant would need to drift, and where it would need to drift toward is the number 1. Stay with what that means for a moment, because it is a startling piece of judgment. Gauss is looking at a formula that beats his own on every number anyone has ever checked, and he is saying calmly that his is better on the grounds of how the error behaves out where nobody can look. He is preferring the shape of a thing over its performance. He is trusting the structure of the mathematics over the evidence in front of him, and he was right. In 1899, more than 4 decades after Gauss died and 91 years after Legendre printed the constant, Charles-Jean de la Vallée-Poussin proved that the best possible constant in Legendre's formula is exactly 1, not 1.08 anything. 1. The fudge factor was an artifact of a table that ran out too early, and an old man in Göttingen had known it from the shape of the error curve alone. Legendre never found out. He had a difficult end, which matters because these men were people and not just names attached to formulas. In 1824 he refused to vote for the government's preferred candidate for a position at the Institute, and his pension was stopped in retaliation. He spent his last years in reduced circumstances and died in 1833. And for nearly 2 centuries afterward, every textbook that printed a portrait of Legendre printed the wrong man, a French politician who happened to share the surname, until in 2005 a scholar tracked down the only authentic likeness anyone has of him. It is a caricature, a quick watercolor sketch made at a meeting of the Institute, showing a stout man with a large nose and an expression of mild impatience. That is the entire visual record of the mathematician who published the first printed statement of a law about the primes. So by the middle of the 1800s, the situation was this. 2 of the finest minds in Europe had independently spotted the same pattern from tables. One of them had the better version and would not print it. Neither had a proof. Nobody had a proof. There was not even a strategy for a proof. and there was a growing suspicion that the problem might not be the kind of thing proofs were for. And this is the point in the story where the popular telling usually cuts, straight from Gauss the boy genius to Riemann the tragic ghost, with the caption saying that nothing much happened in between. Something did happen in between. It happened in St. Petersburg, and the man responsible has been quietly written out of the trailer. Pafnuty Levich Chebyshev was born in 1821 in a village in western Russia into a family of minor gentry. He was born with a defect in one leg that left him with a permanent limp, and by his own account this shaped his entire intellectual life because it kept him out of the running games the other children played. What he did instead was build things. He spent his childhood taking mechanisms apart and putting them back together, and that fascination never left him. In later life, alongside the mathematics that made him famous, he designed and built walking machines, linkages that converted rotary motion into something like a stride, and calculating machines, and a rowing mechanism, and he thought about the geometry of cutting cloth. There is film footage from much later of reconstructions of his linkages walking across a table on jointed brass legs, and they are among the more charming objects in the history of engineering. That is the man who walked into the prime number problem around 1848, and his approach carried the fingerprint of someone who built machines. He did not look for the elegant closed form. He looked for what could be pinned down, tightened, and bounded. Here is what he achieved, and it is far more than the popular version admits. First, he proved a conditional result of surgical precision. Consider the ratio between the true prime count and the simple estimate of a number divided by its logarithm. Nobody could show that this ratio settles down to any particular value as you go out along the number line. Chebyshev proved that if it settles to anything at all, if the ratio has a limit, then that limit must be exactly 1, not approximately 1, not 1.08366, exactly 1. Think about the strange shape of that result. He has not proven the law. He has proven that if the law exists, it has to be the law Gauss guessed, and in doing so, he has closed off every other possibility. It is like a detective who cannot yet prove the suspect was in the house, but has proven that if anyone was in the house, it was the suspect. And consider, in passing, what that does to Legendre's constant. If the ratio converges at all, then Legendre's 1.08366 is already dead, because the only survivable constant is 1. Gauss had reached the same verdict by intuition. Chebyshev nailed it down with a proof. Second, and more concretely, he bracketed the answer. He showed that the true count of primes below any sufficiently large number is squeezed between two explicit multiples of that simple estimate. A lower constant, a little above 9/10, and an upper constant, a little below 1 1/10. In plain terms, he pinned the prime count inside a corridor of roughly 10%, and he did it with real proof, no assumptions, no gaps. Half a century before anyone proved the theorem itself, Chebyshev already knew the answer to within a tenth, permanently and rigorously. And third, in 1852 he proved something that had been floating around as a conjecture since 1845. A claim made by the French mathematician Joseph Bertrand on the basis of numerical evidence. Bertrand's postulate says that for any whole number greater than 1, there is always at least one prime sitting between that number and its double, between 10 and 20, between 1,000 and 2,000, between 1,000,000,000,000 and 2,000,000,000,000. No matter how far out you go, no matter how sparse the primes have become, the corridor from any number to twice that number is never empty. That is a deeply comforting statement, and it has a slightly comic afterlife, because decades later, a young Hungarian wrote a proof of it so short and so charming that it came with a rhyme, which runs in English translation, that Chebyshev said it, and I say it again. There is always a prime between n and 2n. Hold on to the name of that young Hungarian. He comes back into this story much later, in a hallway in Princeton, in the middle of a fight. There is one more Chebyshev result that belongs here, because it is going to matter later, and because it is delightful on its own. In 1853, in a letter, Chebyshev pointed out something odd about the primes when you sort them by what they leave over on division by 4. Every odd prime divided by 4 leaves a remainder of either 1 or 3. 5 leaves 1, 7 leaves 3, 11 leaves 3, and 13 leaves 1. You would expect the two teams to be roughly level, and in the long run they are. But Chebyshev noticed that the team leaving a remainder of 3 is almost always ahead, not by much. But if you stop at any point and count, the 3s are usually winning. This became known as Chebyshev's bias, and it remains one of the loveliest small mysteries in the subject, because the lead is genuinely persistent and genuinely unfair-looking, and it has a real explanation buried in the same machinery we are heading toward. The 3s lead almost all the time, but the lead does change hands infinitely often, and the first time it does is at a number in the 26,000s. Hold on to the shape of that. A pattern that holds for thousands of cases, then fails, then holds again. It is going to come back in a much more dramatic form, so Chebyshev did not close the problem, but he moved it from philosophy into engineering. He proved that there was something there to find, established what it must look like if it existed, and fenced it into a narrow strip. The whole subject then stopped for 7 years because the next move was not an improvement on Chebyshev's method. It was an abandonment of the entire way people had been thinking about primes, made by a shy, sickly, deeply religious young man who wrote 8 pages about it and essentially never mentioned the subject again. Georg Friedrich Bernhard Riemann was born in 1826 in a village called Breschelens in the north of Germany, the second of 6 children of a Lutheran pastor. The family was poor and the children were not healthy. His mother died before her children were grown. Riemann himself was shy to the point of pain, prone to nervous collapse when he had to speak in public, and afflicted from childhood with a chest that never worked properly. He was also, from very early on, obviously extraordinary at mathematics in the specific way that makes teachers uneasy. The director of his school gave him a heavy book on number theory, Legendre's treatise, and Riemann returned it a few days later saying he had finished it. The book ran to well over 800 pages. When quizzed on it weeks afterward, he answered perfectly. He went to Göttingen to study theology, because his father wanted a pastor and Bernhard was a dutiful son. He asked permission to switch to mathematics. His father, to his great credit, said yes. At Göttingen, he sat in Gauss's lectures, though Gauss by then was elderly and famously unenthusiastic about teaching. Riemann went to Berlin, came back, and in 1854 gave the lecture that would eventually reshape physics, a talk on the foundations of geometry that imagined space itself as something that could curve and stretch, a piece of work that sat quietly for 60 years until a patent clerk in Bern needed exactly that language to describe gravity. Gauss, who was not given to praise, is said to have been visibly moved, but the paper that concerns us tonight came 5 years later, and it came about almost as a formality. In 1859, Riemann was elected a corresponding member of the Berlin Academy of Sciences. It was customary on election to submit a paper, a courtesy, a thank you note in the form of research. What he submitted was roughly 8 printed pages under the title, in English, on the number of primes less than a given magnitude. It was the only paper he ever published on number theory in a career of about 15 productive years. He wrote it, sent it, and moved on to other things. It is arguably the most consequential 8 pages in the history of mathematics, and to this day, nobody has fully worked out everything that is in it. Here is what he did, told slowly. Start with something Leonhard Euler had noticed a century earlier, in 1737. Euler was looking at an infinite sum. Take 1, add 1 over 2 raised to some power, add 1 over 3 raised to that power, add 1 over 4 raised to that power, and keep going forever. If the power is bigger than 1, the sum settles down to a finite value. That object is called the zeta function, and it does not look like it has anything to do with primes. It is a sum over all the whole numbers, evenly, with no favoritism. Euler's discovery was that this sum over all numbers is exactly equal to a product over only the primes. One expression running through every integer, another running through nothing but the primes, and they are the same object wearing different clothes. The reason they are equal traces, straight back to Euclid, to the fundamental theorem of arithmetic, to the fact that every number factors into primes in exactly one way. Multiply out the prime side, and unique factorization guarantees that every whole number appears once and only once. Euler deserves a moment of his own here, because he is the reason any of this was available to Riemann at all, and because what he did with that identity is lovely on its own terms. Euler was working in St. Petersburg and later in Berlin, and he was the most prolific mathematician who has ever lived, producing work at a rate that publishers could not keep up with, and continuing to produce it at undiminished speed after he went completely blind in his 60s, dictating to assistants. In 1734 he had solved a famous problem about adding up the reciprocals of the square numbers, 1 plus a quarter plus a ninth plus a 16th and onward forever, and he showed that the answer involves the ratio of a circle's circumference to its diameter, which nobody had expected and nobody could see a reason for. That result made him famous across Europe at 28. 3 years later, he turned the same machinery on the primes, and he asked a question that sounds simple and is not. If you add up the reciprocals of the primes, 1/2 plus 1/3 plus 1/5 plus 1/7 plus 1/11, forever, what happens? For the squares, the sum settles down to a finite number. The squares thin out fast enough that their reciprocals can be gathered into a bounded total. Euler proved that the primes do not. Add up the reciprocals of the primes, and the sum grows without limit. Slowly, painfully slowly, but forever. That is a statement about how thick the primes are, and it is much stronger than saying they are infinite. Plenty of infinite sets are thin enough that their reciprocals converge. The primes are not among them. They thin out, but they never thin out enough to be gathered up, and Euler got that by playing with the bridge between the sum over all numbers and the product over primes, which is to say he got the first quantitative result about prime density out of an identity that Euclid had made possible 2,000 years earlier. So the zeta function is a bridge. On one bank you have the smooth world of continuous sums and calculus. On the other you have the jagged, uncooperative world of the primes. Euler built the bridge and used it to give a new proof that the primes are infinite and, more or less, left it standing there. Riemann's move was to ask what happens if you feed the zeta function a complex number. Complex numbers are the ones with an imaginary part built on the square root of -1, and they are not as exotic as the name suggests. A complex number is just a point on a flat plane instead of a point on a line. It has a horizontal coordinate called the real part, and a vertical coordinate called the imaginary part. Where an ordinary number lives on a road, a complex number lives on a map. Now, the zeta sum only converges, only settles to a finite answer when the real part of the input is greater than 1. Feed it anything else and the sum blows up and tells you nothing, so the function appears to exist only in a strip of the map, off to the right, and to be simply undefined everywhere else. Riemann used a technique called analytic continuation, and the idea behind it may be the loveliest fact in all of mathematics. If a function is smooth in a certain very strong sense, the sense that complex analysis cares about, then its behavior on any small patch determines its behavior everywhere it can possibly be extended. There is exactly one way to continue it. It is like being handed a fragment of a pot from a dig site, and finding that the curvature of the fragment permits precisely one whole vessel and no other. The rim, the base, the width, all of it forced by the shard. So Riemann took the shard of the zeta function that lives to the right of 1 and continued it across the entire complex plane. And once the function existed everywhere, he could ask the question that changes everything: where is it 0? Some of the zeros are dull. There is a family of them sitting at the negative even numbers, -2, -4, -6, marching off to the left forever, and they arrive automatically out of the machinery. Riemann called them trivial, and everyone has called them that ever since, which is a rather brutal thing to do to an infinite family of numbers. The others are not trivial at all. They live in a vertical band, the region where the real part sits between 0 and 1, and they come in pairs above and below the horizontal axis. The first one sits at a height of about 14.1347, the next around 21.02, then 25.01, 30.42, 32.94, and on upward forever, an infinite ladder of points climbing the band. Then Riemann produced the thing that makes this paper immortal, an exact formula for the number of primes. Not an approximation, not a bound, not a statement about limits and ratios, but an exact expression, one side of which is the actual count of primes below any point you like, and the other side of which is Gauss's smooth logarithmic integral, minus a correction term for every non-trivial zero of the zeta function, summed over all of them. Slowly now, because the size of that claim is easy to miss. The primes are the most stubbornly discrete objects in mathematics. They come one at a time, in whole units, with nothing in between. And Riemann wrote down a formula that reproduces their count precisely, using a smooth curve and an infinite orchestra of corrections drawn from the zeros of a function defined on a plane of imaginary numbers. Two worlds that have no business touching, joined by an equals sign. If you know every zero, you know every prime. Not statistically, not on average, but exactly. The primes and the zeros are the same information written in two different alphabets, and buried in the middle of those 8 pages, phrased almost as a passing remark, in a sentence that reads like a man clearing his throat. Riemann noted that it seemed very probable that all of those non-trivial zeros have a real part of exactly 1/2, that they all sit on a single vertical line running up the middle of the band. He said he had made some brief attempts at a proof but had set them aside, since it was not necessary for the immediate purpose of his paper. Not necessary for the immediate purpose of his paper. That sentence is the Riemann hypothesis. It has been open for more than 160 years. It appeared as the 8th problem on David Hilbert's famous list in 1900, the list that set the agenda for the century. Hilbert is supposed to have said that if he were to wake after sleeping 1,000 years, his first question would be whether it had been solved. In the year 2000, it was named one of the 7 Millennium Prize problems, with $1 million attached, which is either a great deal of money or a slightly insulting sum, depending on how you feel about 140 years of collective failure. Thousands of the best minds in mathematics have thrown themselves at it. Entire fields have been invented on the way past it. It stands. But the hypothesis, famous as it is not really the point of what Riemann did. The point is the formula, and to feel what the formula actually says, you have to stop thinking about zeros as points on a map and start thinking about them as sounds. The writer Marcus du Sautoy gave this idea its best name. He called it the music of the primes, and once you have heard the phrase, it is very difficult to think about the subject any other way. Here is the picture. Draw the true prime counting function as a graph. It is a staircase. It sits flat and does nothing across the composite numbers, and every time it reaches a prime it jumps up by exactly 1 and goes flat again. 2, jump. 3, jump. 4, 5, 6, 7, flat, jump, flat, flat, jump. It is a perfect step function, all right angles, rising in unpredictable increments, climbing off to the right forever, like a staircase built by someone with no plan and infinite lumber. Now, draw Gauss's logarithmic integral on top of it. That is a smooth curve, gently rising, no corners anywhere, and it threads through the staircase like a rope laid along a flight of stone steps. It gets the general trend beautifully. It is wrong in the details everywhere, because a smooth curve can never be a staircase. The question that Riemann's formula answers is how you get from the rope to the stone, and the answer is that you add waves. Each non-trivial zero of the zeta function contributes one wave. It is not a metaphor, or rather it is only barely a metaphor, because what the formula actually contains is an oscillating term for every zero, something that rises and falls as you move along the number line, with a frequency set by the height of that zero up the critical band. The low zeros give long, slow swells. The high zeros give tight, rapid ripples. Take Gauss's smooth rope and add the first wave, the one from that first zero, at 14.1347. The rope develops a gentle undulation. It is closer to the staircase now, hugging the steps a little more faithfully but still smooth. Add the second wave. It wobbles more, and the wobble is starting to line up with the steps in a way that feels uncanny. Add 10 waves and the curve is visibly trying to be a staircase, bumping upward near the primes, flattening between them. 100, and it is a staircase with the corners rounded off. 1,000, and you can read the primes off it. Add all of them, every zero out to infinity, and the wobbles stop being wobbles and become the exact right angles of the true count. The rope becomes the stone. That is what Riemann discovered. The primes are the sum of a smooth trend and an infinite set of pure tones. I want to slow this down and do it once more, gently, because this is the single image to take to sleep. Imagine you are listening to a recording of a room, and the recording is muddy, and you want to know what is in it. You have a set of filters, and each filter isolates one frequency. Turn on the first filter and you hear a low hum, and it tells you something, but not much. Turn on the second, and a second tone joins it, and now the two together have a shape. 10 filters in, you can hear that there is a voice. 100 filters in, you can hear which words. 1,000, and you can hear the chair creak and the rain outside and which direction the speaker is facing. Riemann zeros are those filters, and the primes are the room. The first zero, at a height of about 14, gives you the broadest, slowest correction. A long swell that tells you almost nothing about individual primes, but does tell you where the count is running a little ahead or a little behind the smooth curve over enormous stretches. The 10th zero refines that, and the 1,000th adds detail at a much finer scale, resolving where a specific step in the staircase sits. And there is no last zero, so the detail never bottoms out. You can always add another filter, and the picture always sharpens, and only when you have added all of them, infinitely many, does the fuzz resolve into the exact position of every prime that will ever exist. The primes are perfectly determined. In other words, there is no randomness in them at all, and there never was. 2 is prime and always will be. The appearance of randomness is what an infinite orchestra sounds like when you have not yet separated it into its parts. And the astonishing thing, the thing that has kept people at this for 160 years, is that we know the orchestra exists, we know how to describe its instruments, and we still cannot prove the simplest possible fact about where the instruments are sitting. If you have any background in signal processing, or if you have ever seen a chart of a musical note broken into its harmonic content, this will feel familiar, and the resemblance is not an accident. This is a duality of exactly the kind that Fourier analysis lives on. Any sound, however complicated, however rough, can be decomposed into a sum of pure sine waves of different frequencies and strengths, and the collection of those frequencies is called the spectrum. A struck piano string produces a fundamental tone plus a whole ladder of overtones, and the particular mix of overtones is why a piano sounds like a piano and a clarinet playing the same note sounds like a clarinet. The waveform and the spectrum are two complete descriptions of the same event. Neither is more real, you can move between them freely, and physicists and engineers do it 1,000 times a day without thinking about it. The primes and the zeros stand in that same relationship. Think of the primes as the waveform, the thing you hear, the rough irregular signal in time, and the zeros as the spectrum, the hidden ladder of frequencies that produce it. Riemann found the tuning of arithmetic. And I want to be careful here, because this analogy is so satisfying that it is easy to let it do more work than it should. Nobody has ever heard a prime. There is no vibrating object, but the mathematics of the relationship, the actual structure of the formula, is the same mathematics that governs the relationship between a sound and its harmonics. And mathematicians who work in this area use the language of spectra and frequencies and resonance without any embarrassment at all, because it is not decoration. It is the correct vocabulary for the object. Now, with the music in place, go back to the Riemann hypothesis, because it stops being an arbitrary technical condition and becomes something you can almost feel. Every wave has an amplitude, a loudness, a size of the swing it produces. In Riemann's formula, the amplitude of the wave contributed by a given zero is controlled by the real part of that zero, by how far, left or right, it sits in the band. A zero further to the right produces a louder wave, a bigger correction, a larger deviation from Gauss's smooth curve. The band runs from a real part of 0 to a real part of 1. The hypothesis says every zero sits at 1/2, dead center. So the hypothesis is a claim about balance. It says every wave in the orchestra has the same weight. No instrument overpowers the others. every correction term grows at the same modest rate, roughly like the square root of how far along the number line you have traveled, and none of them ever gets to shout. The staircase is built from a chorus in which no voice dominates, and if every wave is that quiet, then the primes never stray far from Gauss's curve. They deviate constantly by amounts of about the square root of the distance traveled, and they come back. Out at a trillion, the square root is a million, and the deviation is a rounding error against the trillion. The primes stay honest. There is a phrase for this in the trade, and it is the one that made the idea click for me. If the hypothesis holds, the primes are as fair as coin flips. Flip a coin a trillion times, and you expect heads about 500 billion times, off by roughly a million, which is the square root of the number of flips. That is what fair randomness looks like, balanced to within a square root rather than perfect balance. And the claim is that the primes, for all their apparent lawlessness, are distributed with exactly that quality of fairness, no better and no worse, from here out to infinity. Now imagine a single zero drifting off the line, just one out of infinitely many, sitting at a real part of 6/10 instead of 1/2. That one zero produces a wave that grows faster than all others. Not dramatically at first, but go far enough and it swamps them. It becomes the loudest voice in the room and everything else becomes accompaniment, and where that wave peaks, the primes bunch up, and where it troughs, they thin out beyond anything the fair coin picture allows. The primes would clump. They would be regions of a number line where they crowd together, and regions where they are strangely absent, and the discrepancy would grow without limit rather than staying inside its square root fence. So the Riemann hypothesis is a statement about whether the primes are well behaved forever, or whether somewhere out past our ability to compute, they begin to gather in drifts like snow against a fence. Everything we have ever measured says they are well behaved. Trillions of zeros have been computed and checked, and every one of them sits on the line at a real part of 1/2, exactly where Riemann said, not approximately, but to the precision of the computation, exactly. Godfrey Harold Hardy proved in 1914 that infinitely many zeros lie on the line, which sounds like a great deal, until you remember there are also infinitely many zeros in total, and infinity divided by infinity is not a comfort. Later work pushed it further, showing that a definite fraction of all zeros lie on the line, first more than a third, then more than 2/5. That is genuine progress. It is also, after 160 years, less than half. And this is the thing about the hypothesis that I find hardest to settle into at night. The difficulty runs deeper than a missing proof. Nobody knows what kind of thing would even count as one. There is no partial root, no clear obstruction, no sense of a wall that we can see and are trying to climb. The best mathematicians alive have described it in various ways as a problem where you cannot tell whether you are one good idea away or a century away, and there is no known method for finding out which. Riemann, who set all of this in motion in 8 pages as a courtesy note to an academy, did not live to see any of it. He had 7 years left and he spent most of them ill. Tuberculosis in the 1860s was not a disease you survived. It was a disease you managed, and the management consisted almost entirely of going somewhere warm. So Riemann went to Italy 3 times in the last years, travelling south to Pisa and Rome and the lakes, working when he could, and coming back north each time a little weaker than he had left. On the final trip he did not come back. He died on the 20th of July 1866 at Salasca, a small place on the western shore of Lake Maggiore in the north of Italy, where the mountains come down close to the water and the light on the lake in the evening is the sort of thing people travel a long way to see. He was 39 years old. His friend Richard Dedekind wrote the memoir that gives us most of what we know about the end. By Dedekind's account, Riemann was working to the last, sitting outdoors under a fig tree, in full possession of his mind, taking great pleasure in the view over the water. He was leaving a piece of work unfinished. His wife was with him. He was buried in the churchyard at Biganzolo nearby, and the gravestone has since been moved, and the cemetery wall was rebuilt at some point. And there is a certain amount of confusion in the record about exactly where the grave now is, which feels grimly appropriate for this particular man. Back in Göttingen, meanwhile, something happened that mathematicians have been grinding their teeth about for a century and a half. Riemann's housekeeper, faced with a dead man's study full of paper, did what housekeepers did with dead men's paper. She burned a large quantity of it, notes, drafts, calculations, working sheets, whatever was in the piles. There was no malice in it, and no stupidity either, only a tidy person clearing a room. But by the time his colleagues intervened and rescued what was left, an unknown quantity of the working notes of one of the deepest mathematical minds who ever lived had gone up the chimney of a house in a German university town. Among the things believed lost is a small black notebook containing records of his stay in Paris in the spring of 1860. That is the year after the great paper. Whatever he was thinking about the primes in the months after he wrote those 8 pages, whatever he tried and abandoned and half saw, was probably in that book. What survived was gathered into the university library at Göttingen and is known by the German word for a literary estate, the Nachlass. It is a heap of rough working papers, unsorted in Riemann's private handwriting, dense with abandoned calculations and no explanations, and for decades it sat there while the mathematical world formed a settled opinion about the man who wrote it. That opinion, which stands as one of the great misjudgments in the history of the subject, was that the 8-page paper was mostly bluff. You can see how they got there. Riemann's paper asserts a great deal and proves comparatively little. He states results and moves on. He says things are evident that took later mathematicians decades to establish. The estimate for the number of zeros up to a given height, the convergence of his exact formula, the claim about how many zeros lie on the critical line, all of it presented with a confidence that is not backed up on the page. Edmund Landau, one of the most rigorous analysts of his generation, took the view that the paper was closer to a program of conjectures than a piece of finished mathematics. Hardy, in England, held a similar line. The consensus hardened. Riemann was a visionary, yes, but he had guessed, and the guesses had happened to be brilliant, and the actual work of proof belonged to the people who came after. In 1926, a mathematician named Erich Bessel-Hagen, working in Göttingen, was going through the Nachlass and found an approximate formula in Riemann's notes that nobody had known was there. It was closely related to something Hardy and Littlewood had derived with enormous effort in the 1920s. Riemann had it 60 years earlier and had said nothing. That discovery was the loose thread, and the man who pulled it was Carl Ludwig Siegel. Siegel was in his 30s, a superb analyst with a scholar's patience, and he did something nobody else had been willing to do. He sat down with the Nachlass and tried to actually read it, not skim it, read it, reconstruct the reasoning behind the scribbles, fill the gaps, work out what the man had been doing. This took him about 2 years. 2 years of deciphering private handwriting, chasing calculations that break off mid-page, reconstructing arguments from fragments. It stands as one of the great acts of scholarship in mathematics, and it is largely unsung, because reconstructing someone else's work does not carry the glory of doing your own. What Siegel found and published in 1932 in a paper on Riemann's estate as it relates to analytic number theory rewrote the reputation of the 8-page paper permanently. Riemann had not been guessing. Buried in those rough sheets was a method for computing values of the zeta function, an asymptotic formula of real sophistication, far better than anything available in 1932. 60 years of the finest analysts in Europe had not found it. It had been sitting in a library in Göttingen the entire time, in the handwriting of a dead man, unpublished and unmentioned. Once Siegel worked it out and put it in usable form, it became the standard tool for the numerical hunt for zeros, and it is still called the Riemann-Siegel formula, which is the correct and slightly heartbreaking name for it. And there was more because Riemann had used it. He had actually run the calculations himself by hand on paper. In among the working sheets were the numbers, the actual hand calculations, and from them he had located the first zeros of the zeta function. His value for the first zero was 14.1386. The true value is 14.1347. He was off in the 3rd decimal place, working by hand with a method of his own invention on a problem where nobody else on earth could compute anything at all. He also confirmed it was the first, with nothing below it, and got the 2nd and 3rd to within a percent or so. So when Riemann wrote in his paper that it seemed very probable all the zeros lie on the critical line, He was not making a poetic leap. He had a method. He had run it. He had the numbers on the desk in front of him. The published paper was the polished exterior. The machinery was in the notes, and he did not think it was worth printing. That is a fact I find difficult to be at peace with, and I say that as someone who admires restraint. Gauss withheld because things were not ripe. Riemann seems to have withheld because it did not occur to him that anyone would need it. Between the two of them, the two greatest arithmeticians of the 19th century, an enormous amount of mathematics was simply not communicated, and the rest of the field spent decades walking uphill in the dark on ground that had already been surveyed. And, of course, the housekeeper. Siegel found what he found in the papers that survived. Nobody knows what was in the ones that did not. The necklace has been picked over many times since, and it keeps yielding. There are still sheets in that collection whose purpose is unclear. Every so often, someone returns to it with a new set of questions and finds something. It is one of the few places in mathematics where the archive is still a live source rather than a museum. But with the Riemann-Siegel formula in hand, the hunt could finally begin properly, and the hunt for the zeros of the zeta function turns out to be one of the strangest computational stories of the 20th century, because among the people who took it up was a man who wanted to prove the whole thing false, and who tried to do it with brass gears in a suitcase. Before the machines, there were people, and what those people managed by hand is difficult to credit. The Danish mathematician Jorgen Pedersen Gram published 15 zeros in 1903, computed by hand, and every one of them sat on the critical line. The Finn Ralph Backlund got it to 79 by 1914. An American named John Hutchinson reached 138 in 1925, grinding through the arithmetic on a Monroe calculating machine, one of those beautiful heavy office devices with rows of keys and a crank on the side that you turned to make the carriage advance. Then Siegel published Riemann's method, and the whole enterprise accelerated. Edward Titchmarsh at Oxford obtained a grant for a larger effort in the mid-1930s, and what he assembled deserves describing properly, because it is a picture of what computation looked like before the word meant a machine. He had the Riemann-Siegel formula. He had punch-card tabulating equipment borrowed from the astronomical world with the help of Leslie Comrie, and he had a team of human calculators, who in those days were called computers, and who were mostly women working from printed tables and instruction sheets. Between them they verified 1041 zeros, all on the line, and that is where a young man at Cambridge came in, with an idea that has to be one of the strangest engineering projects of the 20th century. Alan Turing had been interested in the zeta function since he was a student. He had already written the paper on computable numbers that founded theoretical computer science, and having settled the decision problem he was looking for another mountain, and there was no bigger one available, but Turing's interest had a particular flavor that separates him from nearly everyone else in this story. He wanted to prove it false. Turing appears to have genuinely suspected the Riemann hypothesis was wrong, not out of contrarianism, but because he was the kind of person who thinks that a statement everyone believes and nobody can prove is a statement worth attacking from the other side. And he reasoned that if a zero did sit off the line, you might find it by climbing high enough up the ladder and looking, and the way to climb was to compute, and the way to compute faster was to build a machine. So in 1939 he applied to the Royal Society for a grant of £40 to build one. £40. To settle the greatest open problem in mathematics. The scale of that request is magnificently English. He got the money, and the machine he designed was not electronic, because in 1939 essentially nothing was. It was an analog device, a mechanical calculator built out of gear wheels, and the inspiration for it came from an unlikely place. Turing knew about the tide predicting machines used in Liverpool, elaborate brass assemblies that summed up the harmonic components of the tides by turning wheels of carefully chosen sizes and reading off the total. The mathematics of predicting a tide involves adding a series of trigonometric terms. So does computing the zeta function on the critical line. Different physics, same shape of sum. He did the engineering himself, which is the part I love. He took the gear blanks in a rucksack across to the engineering department at Cambridge, cut the wheels there, and carried them back to his rooms where they lived on the floor and in a suitcase. Most of them got cut. There is a blueprint in the archive dated the summer of 1939, and there are photographs of the surviving gears, and there is not, and never was, a finished machine, because in September of 1939 the war began, and Turing went to Bletchley Park, and the gears stayed in the suitcase for the duration. By the time he came back to the problem, the world he had helped invent had made his brass wheels obsolete. In June of 1950, he used the Manchester University Mark I, one of the first stored program electronic computers, to run the calculation properly. He pushed the verified count from Titchmarsh's 1041 to 1004. Along the way, he also developed a technique for proving that no zeros had been missed between the ones you found, a method still called Turing's method and still used today. He found no counterexample. He wrote up the calculation in a paper published in 1953 and noted with some understatement that the work had been planned well in advance, but had in fact been carried out in great haste, which is a sentence anyone who has ever booked time on shared equipment will recognize with a certain sympathy. The hunt continued, and it never really stopped. Derek Lemmer reached 25,000 zeros in 1956. Rosser and his collaborators reached 3.5 million in 1968. A Dutch group in 1986 checked the first 1.5 billion. By the mid-2000s, Gordon and Demichel had verified the first 10 trillion. 10 trillion zeros, every one of them sitting on the line, at a real part of exactly 1/2, precisely where a dying man in 1859 said they would probably be. And it proves nothing. That is the thing you have to keep hold of. 10 trillion is a rounding error against infinity, and there are results in number theory where the first counterexample turns up in regions so far out that no amount of computing could ever have found it, which, as it happens, is exactly what we are going to run into shortly. There is a story about Hardy that belongs here, because it is the funniest thing in this entire subject, and it tells you something true about how these people lived with the problem. Hardy spent summers in Denmark with his friend Harold Bohr, and at the end of one visit he had to cross the North Sea in a small boat in genuinely bad weather. Hardy, a lifelong atheist who nonetheless maintained a long-running personal feud with God, took out a postcard before boarding and wrote on it that he had proved the Riemann hypothesis. Then he posted it. His reasoning was that God would not permit him to drown having achieved such undeserved glory, and would therefore have to see him safely across in order to deny him the satisfaction. He arrived intact, and he always said the postcard was what did it. If you are enjoying this, subscribe. There is more of this kind of thing on the way. Now, everything so far has been the approach. 200 years of counting, bracketing, conjecturing, and building machinery, and still nobody had proved the thing that a 15-year-old had written in a table of logarithms. That changes in 1896, and it changes twice in 2 different countries in the same year by 2 men who had never coordinated. Jacques Hadamard was French, born in 1865, a Parisian, and he had spent years on a problem that looked like pure abstraction. He was studying entire functions, the well-behaved functions of a complex variable, and specifically how you can reconstruct such a function from the places where it vanishes. It is the kind of investigation that has no obvious application until suddenly it has exactly one. Hadamard's work on that problem, published in 1893, gave him tools for handling the zeros of the zeta function that nobody else possessed, and he had built them, by his own account, largely in order to put Riemann's assertions on a firm footing. Charles Jean de la Vallée-Poussin was Belgian, born in 1866, the son of a professor of geology at Louvain, and he came at it independently, from a different direction, with different technique. In 1896, both of them proved the prime number theorem. Separately, in the same year, neither knowing what the other was doing. The theorem itself, stated plainly, is that the count of primes below a given number, divided by that number over its natural logarithm, approaches 1 as you go out along the number line forever, which is precisely what Chebyshev had shown must be the case if it approached anything at all, and precisely what Gauss had written down in the margins of a book of tables at 15. The key that unlocked it, in both proofs, was a statement about where the zeros are not. The real part of a zero sets how loud its wave is, and the band runs from 0 to 1. A 0 sitting at a real part of 1, right at the edge, would produce a correction term growing just as fast as Gauss's main term itself. It would be a voice as loud as the melody. And if such a wave existed, the ratio at the heart of the theorem would never settle down, because there would always be something oscillating at full strength forever, refusing to fade into the background. So the whole theorem comes down to a single question: is the edge of the band clean? Both men prove that it is. No 0 of the zeta function sits on the line where the real part equals 1. Every non-trivial 0 lives strictly inside the band, which means every correction wave grows strictly slower than the main term, which means that if you go far enough out, the corrections fade relative to the trend, and the trend is Gauss's curve. And that is the proof, not a formula for the primes, and not a way to find them, but a demonstration that a certain vertical line on a plane of imaginary numbers is empty, and that this emptiness, propagating through Riemann's machinery, forces the primes to thin out at the rate a teenager guessed 104 years earlier. Think about the distance that argument travels. You want to know how many primes are under 1,000,000. The answer arrives by way of an infinite sum extended onto the complex plane, and a statement about which points on that plane a certain function fails to be 0 at. There is no shorter road. Hadamard himself is often quoted saying that the shortest path between two truths in the real domain passes through the complex domain, and this is the example he had in his hands when he said it. De la Vallée-Poussin then went further. He worked out how fast the approximation converges, giving an error term, which is the difference between knowing that two things eventually agree and knowing how impatient you are allowed to be about it. And in 1899 he settled the matter of Legendre's constant, proving that the correct value is 1, exactly as Gauss had judged from the shape of the error curve half a century before, without a proof, with nothing but taste. So it closed. 104 years from a boy with a table to a theorem with a name. And there is a small, warm coda to 1896 that mathematicians have enjoyed for over a century. Hadamard died in 1963 at the age of 97. De la Vallée-Poussin died in 1962 at 95. Two men, born a year apart, who proved the same theorem in the same year and who both lived very nearly a century, dying within a year of each other at the far end of it. This produced a running joke in the number theory community that proving the prime number theorem confers long life, offered as a serious research incentive to graduate students ever since. Hadamard's own long life was not gentle. He lost 2 sons in the First War and a third in the Second, and he spent his later years working for peace and for scientific cooperation across borders that had recently been trenches. There is a photograph of him in old age, a small, neat man with a white beard and an expression of enormous patience. Behind every name attached to a theorem there was a person carrying that much. Now, here is where the popular version of this story ends. Boy sees a pattern. A century passes, theorem proved, a pleasing arc with a satisfying close, and every article and video that covers this material tends to stop somewhere around here, with a line about how it took 100 years to prove what Gauss saw at 15. But 1896 is not the end of the story. It is barely the middle, because the 3 most interesting things that ever happened to the prime number theorem all happened afterwards, and the first of them arrived 18 years later from Cambridge, and it demolished something everybody had assumed was obviously true. Go back to Gauss's curve lying along the staircase and look closely at how it sits. For every number anyone had ever checked, the logarithmic integral came out slightly too high. It overshot. It predicted a few more primes than were actually there, every time at every scale without exception. Below 100, too high. Below 1,000,000 and below 1,000,000,000, still too high. Out at 100 trillion, too high again. The gap wobbles in size but never changes sign, and by the early 20th century the tables ran far enough that the pattern looked less like a pattern and more like a law. Gauss thought the inequality was strict, and said so. Riemann thought so. It is difficult to find a 19th century mathematician who doubted it. When something holds for every case you can compute, across many orders of magnitude, with no sign of weakening, the human mind stops treating it as an observation and starts treating it as a fact. There is even a good reason for the bias, once you know where to look, and it is a satisfying one. Riemann's exact formula does not compare the prime count directly to the logarithmic integral. It compares a slightly different quantity, one that counts the primes, but also gives a smaller partial credit to the squares of primes, and a still smaller credit to the cubes, and so on down. 4 is not prime, but it is 2 squared, and in Riemann's accounting it contributes a fraction. 8 contributes a smaller fraction, 9, 25, 27, all of them contributes a little. So the logarithmic integral is not really estimating the primes. It is estimating the primes plus a modest tax paid by the prime powers, and since the prime powers really are there, and Gauss's curve is unknowingly counting them, the curve comes out high. The correction is roughly half the logarithmic integral of the square root, which is small but persistent, and it biases the whole comparison in one direction from the very beginning, which makes it feel even more settled. There is a mechanism, the overshoot has a cause, and the cause is not going anywhere. Then, in 1914, John Edensaw Littlewood proved that the overshoot fails. Littlewood was Hardy's collaborator at Cambridge, one half of the most productive partnership in the history of mathematics, a man who worked with such intensity that he suffered a decades-long depression and did some of his finest work afterwards in his 70s. What he proved is this: the difference between the true prime count and Gauss's estimate does not merely fail once, it changes sign infinitely often, infinitely many times. Out along the number line, the primes actually overtake the curve, and infinitely many times they fall back behind it, forever, in both directions, without end. The overshoot everyone had accepted as permanent is a temporary condition. It is the opening bars of a piece of music that swaps back and forth an infinite number of times, and we have only ever heard the first note. Then comes the part that turns this from a good result into one of the strangest situations in mathematics. Littlewood's proof does not tell you where. Not approximately, not within a factor of a billion, not at all. It is what is called an ineffective proof, one that demonstrates that something must exist without giving any means of locating it, or even bounding where you might start looking. He proved there is a crossing. He could not point at a single one, and his method could not be squeezed to produce one. That situation is unusual enough that it was not obvious at the time whether the question was even meaningful to ask. So it fell to Littlewood's student, a South African named Stanley Skews, to make the existence proof effective, to put a ceiling on it, to say, at minimum, that the first crossing happens somewhere below here. In 1933, assuming the Riemann hypothesis is true, Skews produced that ceiling. The number is 10 raised to the power of 10 raised to the power of 10 raised to the power of 34. Take a moment with that, because the notation slides past the ear far too easily. Start with 10 to the 34th, which is a 1 followed by 34 zeros, a number already larger than the count of stars in the observable universe by a comfortable margin. Now raise 10 to that power. You have a number with more zeros in it than there are atoms in the earth. Now raise 10 to that. There is no physical comparison left to make. There is not enough matter, not enough space, not enough time in the history of the universe to write the number down, even if every particle were a digit and you had been writing since the beginning. That was the upper bound. That was where Skews could promise the primes overtake Gauss's curve at least once before. Hardy is supposed to have remarked that it was the largest number that had ever served any definite purpose in mathematics, and for decades that was simply true. It held the title until the 1970s, when work in combinatorics produced quantities that make Skews look like a pocket calculator error. But for its era, it was the undisputed monster, and it entered popular mathematics as the Skews number, the number so big that it broke people's intuitions about what a proof could contain, and note what it rests on. That bound assumes the Riemann hypothesis. In 1955, Skews came back and produced a second bound that assumes nothing, and, as you might expect from a proof that has been given less to work with, it is very much larger, roughly 10 to the 10 to the 10 to the 963, if you insist on a comparison, though even writing that as an approximation involves some quiet arithmetic sleight of hand. Since then, the bounds have come down enormously. Riemann improved it in the 1960s. Hermann Terreal brought it down dramatically in 1987. Bayes and Hudson, working with the first million pairs of zeta zeros, showed in the year 2000 that there are values of the number line near roughly 1.4 times 10 to the 316th power where the primes do get ahead. Later refinement by Demichel pinned the likely first crossing at about 1.397 times 10 to the 316th. 10 to the 316th is still not a physical number. It is vastly beyond the count of atoms in the observable universe, which sits somewhere around 10 to the 80th. But it has come down from something unimaginable to something merely absurd. And that is progress. And here is the part I keep turning over. We still do not know the answer. Nobody has ever exhibited a single number where the primes beat Gauss's estimate. Not one. We know there are infinitely many. We know roughly where the first one probably lives, and we have a lower bound telling us it sits above 10 to the 19th, so there is no point looking down here. But the actual integer, the specific place on the number line where a boy's curve fails for the first time, has never been written down by anyone, and given where it sits, it may never be. Now, why does the crossing happen at all? Come back to the waves. That prime power bias is a steady, quiet pressure holding Gauss's curve above the true count, growing like the square root divided by the logarithm. The correction waves from the zeros are all oscillating around it, each one rising and falling, mostly cancelling each other out because their frequencies are unrelated. Ordinarily, their combined effect is smaller than the bias, so the bias wins and the overshoot holds. But they are waves, and waves, given long enough, will occasionally line up. Somewhere out there, an enormous number of these oscillations happen to reach their peaks at roughly the same moment, and their combined push exceeds the steady pressure of the bias, and for a stretch of the number line the primes come out ahead. Then the alignment falls apart, the waves scatter back into incoherence, and the overshoot resumes as though nothing happened. It is a resonance. It is the same phenomenon as a great many small ripples happening to combine into one large wave in an ocean, which is rare and unpredictable and absolutely certain to happen eventually if you wait. So the first great correction to the popular story is this. Gauss's estimate, the thing the whole 100-year quest was aimed at proving, is not merely approximate. It is provably wrong, infinitely often, in a place no human being has ever been able to locate. And the second correction is about a friendship. For 50 years after 1896, one belief sat at the center of analytic number theory and was more or less never questioned. To prove the prime number theorem, you had to go through the complex plane. You had to use the zeta function, the analytic continuation, the whole apparatus Riemann built. There was no other road, and the reason people believed this was not laziness. It was that the theorem seemed to be about the complex plane, in some deep sense, and that the connection was not a technique but a fact about the world. Hardy put it about as strongly as it can be put. He said that if anyone were to produce an elementary proof of the prime number theorem, one avoiding complex analysis altogether, it would show that our whole sense of how these ideas hang together was wrong, that the subject did not fit together the way we supposed, and that it would be time to set the books aside and rewrite the theory from scratch. The word elementary, in this context, does not mean easy. It is among the more misleading pieces of vocabulary in mathematics. An elementary proof means one that stays inside the ordinary numbers and does not detour through the complex plane. Such proofs are frequently longer, harder, and more technically brutal than the analytic ones they replace. Elementary means low altitude, not easy walking. In 1948, at the Institute for Advanced Study in Princeton, a group of number theorists were in residence at the same time. Attila Selberg, Paul Erdos, Paul Turan, and Sarvadaman Chawla. 4 people, 1 building, a common room and a lawn, and a great deal of walking and talking. Selberg was Norwegian, born in 1917, and he was among the most solitary mathematicians of his century. During the German occupation of Norway, he had been almost completely cut off from the international community, working alone in Oslo, and he produced extraordinary results in that isolation. He was not unfriendly by all accounts, but he worked by himself, on his own problems, at his own pace, and he did not naturally think in terms of collaboration. Erdos was his precise opposite, and one of the most singular human beings mathematics has ever produced. Hungarian, born in 1913, he had no home, no job, and eventually almost no possessions. He travelled continuously for decades, arriving at colleagues' houses with a suitcase, announcing that his brain was open, working for a few days and moving on. He wrote papers with more than 500 collaborators, and he called children epsilons after the mathematical symbol for a small quantity. And he spoke of a book held by a deity he did not believe in, containing the most beautiful proof of every theorem, and the highest praise he could give an argument was that it came straight from the book. And here is the detail that closes a loop we opened much earlier. Erdős's very first published paper, written in 1932 when he was 19 years old, was an elementary proof of Bertrand's postulate, the result Chebyshev had proved in 1852, that there is always a prime between a number and its double. A teenager in Budapest had found a proof so clean that it is still the one taught, and it came with that little rhyme about Chebyshev saying it and Erdős saying it again. 16 years later he was in Princeton, and the same corner of mathematics was about to hand him the fight of his life. What set it off was that Selberg had found something. He had derived a formula, an identity relating sums over primes to each other, which he called the fundamental formula, and which is now generally known as Selberg's symmetry formula. It is entirely elementary in the technical sense, no complex analysis anywhere in it, and it had a curious quality. It clearly contained real information about the density of primes, more than anything elementary that had come before, but it was not obvious that it contained enough to reach the prime number theorem. Selberg had a door, and he could not tell whether there was a room behind it. He mentioned the formula to some colleagues. Turan, who was a close friend of Erdős, heard about it and passed it on. And Erdős, who was constitutionally incapable of leaving an interesting formula alone, took it and ran. Within days he had used it to prove a substantial new result about the density of primes in short intervals, a generalization of exactly the sort of thing Chebyshev and Bertrand had been after. He showed the working to Selberg. Selberg looked at it and, by his own later account, told Erdős the next day that he could use that result to complete the whole thing, to get the prime number theorem, elementarily. And around the same time he found the additional argument he needed by another route as well, so in the space of about a week, the impossible had happened. A proof of the prime number theorem with no complex analysis in it at all, built out of Selberg's formula and Erdős's insight and Selberg's finish. It should have been one of the great shared moments in 20th century mathematics. Two of the sharpest minds alive, in one building, closing a 50-year-old question that the field's most authoritative voice had declared essentially out of reach. What happened instead was a quarrel that neither of them ever fully recovered from. The dispute was about publication. Erdős, whose entire mathematical life was built on collaboration, assumed a joint paper. When Selberg proposed publishing separately, Erdős suggested they handle it the way Hardy and Littlewood had handled their long partnership, with everything joint regardless of who did which piece. Selberg preferred to publish alone, believing the core of the proof was his. And underneath the practical question sat something harder, which is that Erdős talked. He was a man who spread news of mathematics the way weather spreads. He had written to colleagues about the result, mentioned it in seminars, told people at other institutions. Selberg, from Syracuse, where he had just taken a position, began hearing that the elementary proof was being described as Erdős's, with his own name attached as a secondary contributor. And for a man who had spent the war working in total isolation and knew exactly what his own hands had built, that was intolerable. The mathematician Ernst Strauss, who was there, summarized the whole thing in 4 words that have been quoted ever since. Alas, something had gone wrong. They published separately in 1949. Selberg's paper appeared in the Annals of Mathematics, Erdős's in the Proceedings of the National Academy of Sciences. The papers acknowledge each other. The men did not work together again. In 1950, Selberg received the Fields Medal, the highest honor in mathematics, cited for the elementary proof among other work. In 1951, Erdős received the Cole Prize in number theory, largely for the same episode. Both went on to long and enormously productive careers. Selberg stayed at the Institute for Advanced Study for the rest of his life and made contributions that still dominate whole areas. Erdős kept traveling, kept collaborating, kept opening his brain in other people's living rooms until he died in 1996 at a conference in Warsaw, which is exactly how he would have chosen it. But they had touched the same theorem at the same moment, and it cost them. And there is a final irony that I find quietly devastating. The elementary proof, once the dust settled, did not do what Hardy feared. It did not force anyone to rewrite the theory, nor did it replace the analytic proof, which remained shorter and cleaner and gives far better error terms. And it shed no light at all on the Riemann hypothesis, which stands exactly where it stood before. It proved that the road through the complex plane was not the only road, which is a genuine and beautiful thing to know, and it turned out to be a scenic route rather than a shortcut. Two of the finest mathematicians of the century lost a friendship over a proof that changed less than everyone expected. That happens. It happens more often than the tidy version of scientific history likes to admit. But the third correction to the popular story is not about people at all. It is about what the primes turned out to be made of, and it arrived by accident, over a cup of tea, because one man would not stop insisting on an introduction. Early April 1972, the Institute for Advanced Study in Princeton, a low building set among lawns and woodland, with a pond at the back and a common room in Fould Hall where, every afternoon, they serve tea. The tea at the Institute is an institution within the institution. It is not optional in spirit, even though it is optional in fact. The entire architecture of the place is designed around the theory that if you put brilliant people in a room with hot drinks and nothing scheduled, useful collisions will occur. This is one of the very few times in the history of that theory when it worked so spectacularly that people are still telling the story half a century later. Hugh Montgomery was in his mid-20s, an American number theorist, and he had spent the previous year at the Institute as a member. He was back for a short visit, and the reason he had come was to show a new result to Atlas Selberg. The same Selberg, 24 years on from the fight with Erdos, now a permanent professor in the School of Mathematics and one of the great authorities on the zeta function alive. Montgomery's result concerned the spacing between Riemann's zeros. Everyone knew the zeros climbed the critical line, and everyone knew roughly how densely they were packed, because Riemann himself had estimated that. What nobody had examined properly was the finer question. Given the zeros, how are they arranged relative to each other? If you take two of them at random, how likely is a particular gap? Are they scattered like raindrops on a pavement, independently, with no regard for each other? Or is there structure in how they space themselves? Montgomery had worked out a formula for what is called the pair correlation, which is the mathematical description of exactly that. And what his formula said was that the zeros are not independent. They avoid each other. There is a repulsion between them. Finding two zeros very close together is far less likely than pure chance would suggest, as though each zero were pushing gently against its neighbors to keep a little space clear. He took tea that day with Chowla. Savadaman Chowla was an Indian-born number theorist, warm and sociable and, by every account, entirely relentless in the business of introducing people to each other. Freeman Dyson was standing across the room. Dyson was among the most celebrated physicists in the world, the man who had unified the competing formulations of quantum electrodynamics, an Englishman at Princeton with a reputation for being able to see through any problem put in front of him. Montgomery had spent a year at the Institute and knew him perfectly well by sight, and had never spoken to him. Chowla asked whether he had met Dyson, and Montgomery said no. Chowla said he would introduce them, and Montgomery, by his own retelling many years later, said that he did not feel he had to meet Dyson. He was a young number theorist. Dyson was a physicist of enormous stature. There was no particular reason for the conversation, and Montgomery had no wish to impose. Chowla insisted, and Montgomery has described what followed as being dragged reluctantly across the room. Dyson was polite and asked the standard question, "What are you working on?" Montgomery said he was working on the differences between the non-trivial zeros of Riemann's zeta function, and that he had developed a conjecture about the distribution of those differences, and he began to describe the formula. And Dyson, before he could finish, said something to the effect of, "Extraordinary," and either wrote the formula down himself or recognized it instantly on the board, depending on which version of the story you read. Every version agrees on what he said next. That is the pair correlation function for the eigenvalues of a large random Hermitian matrix. It is also the model for the energy levels in a heavy nucleus, uranium-238 for instance. Now let me explain what Dyson was recognizing, because this is the moment the whole story has been walking toward. In the 1950s, physicists had a problem with heavy atomic nuclei. A nucleus containing 238 particles, all interacting with each other through forces nobody could write down exactly, is not a system you can solve. The equations exist in principle and are useless in practice, but you can measure such a nucleus. You can fire neutrons at it and observe the energy levels at which it resonates, and those levels come out as a long list of numbers, hundreds of them, climbing upward, and each one is a fact about a system too complicated to compute. Eugene Wigner proposed something that sounds, at first hearing, like giving up. If you cannot write down the true equations, replace them with a random matrix. Fill a large grid with random numbers, subject only to the symmetry conditions that quantum mechanics requires, and compute its eigenvalues, which are the characteristic numbers that a matrix carries the way a bell carries a pitch. Do this many times and study the statistics of those eigenvalues. It should not have worked. It worked beautifully. The statistical pattern of eigenvalues from random matrices matched the measured energy levels of heavy nuclei with startling accuracy, not the individual levels, which are specific to each nucleus, but the pattern of the spacings, the way the levels distribute themselves relative to their neighbors. And the most distinctive feature of that pattern is repulsion. The energy levels of a heavy nucleus avoid each other. They do not cluster the way independent random points would. They keep their distance. Dyson had spent about a decade working on the mathematics of exactly this, mostly through the 1960s, developing the theory of these random matrix ensembles. He knew that pair correlation function the way you know a song you have played every day for 10 years. And a young man had just walked across a common room in New Jersey and written it on a blackboard, having derived it from the zeros of a function invented to count prime numbers. Let the size of that settle for a moment. The primes are the oldest objects in mathematics. They were studied in Alexandria. They require no physics, no experiment, no universe, and they would be exactly what they are in a cosmos with different constants or no matter at all. And the hidden frequencies that generate them, the zeros of Riemann's zeta function, turn out to be arranged according to the same statistical law that governs the energy levels inside a lump of uranium. The zeros repel each other in precisely the way quantum energy levels repel each other. Same formula, same curve, and no known reason at all. The obvious next step was to check it numerically, and that fell largely to Andrew Odlyzko at Bell Labs, who spent years computing zeros at heights that beg a description. Not the first few thousand. Zeros in the neighborhood of the 10 to the 20th zero, and higher still, out to regions around the 10 to the 22nd and 10 to the 23rd. And he compared their spacing statistics against the random matrix predictions. The agreement is extraordinary, not merely suggestive or broadly consistent, but the kind of agreement that makes physicists nervous. Curves lying on top of each other across the whole range, with deviations you have to work to see. Somebody nicknamed the resulting body of data the spectrum of Riemannium, as though we had discovered an element and were measuring its emission lines, and the joke stuck because it is not really a joke, which brings us to a hope that predates all of this by 50 years, and that now has evidence behind it. Early in the 20th century, David Hilbert and George Polya, apparently independently, floated an idea about why the Riemann hypothesis might be true. Suppose the zeros are not merely numbers. Suppose they are the eigenvalues of some operator, some mathematical object of the kind that quantum mechanics is built from, with the particular symmetry property that guarantees all its eigenvalues are real numbers. If such an operator exists, then the zeros are forced onto the critical line automatically, not as a coincidence but as a consequence of the symmetry, and the hypothesis follows. Nobody has found the operator. It is not for lack of looking, but since that afternoon in Fold Hall, the search has had a shape to it, because the statistics tell us what kind of operator to look for. Whatever it is, it behaves like the energy operator of a quantum system whose classical version is chaotic. The primes, on this reading, would be the observable spectrum of some hidden system we have not yet identified, humming away underneath arithmetic, obeying the same rules as an atomic nucleus. Montgomery, decades later, added a small human coda to the story. He said that to this day he had spoken with Dyson exactly once and received exactly one letter from him. One conversation, one letter, and a connection between prime numbers and quantum physics that has occupied a generation of mathematicians and shows no sign of closing. So let me put the whole thing back together, because the shape of this story matters as much as the facts in it. The version you'll usually meet goes like this. A boy of 15 looked at a table of numbers and saw a law. Nobody could prove it for over a century. Then, in 1896, 2 men proved it, and the boy was vindicated. And the moral is that raw data honestly examined will reveal the truth to a sufficiently patient eye. It is a good story. It is even mostly true. But it puts the finish line in the wrong place, and in doing so, it hides everything that makes this subject worth staying awake for, or, given the hour, worth falling asleep to. The prime number theorem was never the destination. It was the doorway. Here is the distinction, and it is the thing I would want you to carry out of this. Gauss's curve is not a description of the primes. It is a description of the average of the primes. It tells you the trend, the long-term thinning, the shape of the crowd, and says nothing whatsoever about any individual prime. And it was never going to, and proving it correct in 1896 settled the trend and left everything else exactly as open as it had been. The primes themselves are made of something else. They are made of Riemann's waves. The staircase is not the smooth curve with noise on top. The staircase is the smooth curve plus an infinite orchestra of pure tones, each one contributed by a zero of a function on the complex plane. And every jagged step of that staircase, every gap, every twin pair, every stretch of emptiness is the sound of those tones adding and cancelling. When you ask why there is a prime here and not there, you are asking about the waves. Nothing about 1896 touches that question. And once you frame it that way, the 3 great episodes after the proof stop looking like footnotes and start looking like the actual body of the story. The first is that Gauss's estimate, the very thing that was proved, is provably wrong. Not slightly imprecise, wrong in the direction everybody thought was impossible, infinitely many times, at a place that a century of work has failed to locate. The first number where the primes overtake that beautiful curve has never been written down and may sit somewhere near 10 to the 316th power, out past every atom in the universe, waiting. The second is that the shortcut everybody said could not exist, did exist, that 2 extraordinary people found it in the same building in the same week, and that it cost them their friendship and gave the field rather less than it had promised. As it happens, the road through the complex plane turned out not to be the only road. It also turned out to be the better one. And the third is that the zeros, the hidden frequencies underneath all of arithmetic, are arranged according to the same statistics as the energy levels of a uranium nucleus. That one is still open. Nobody has explained it. It may be the deepest hint anyone has ever had about what the primes actually are. And it arrived because a man named Chowler would not take no for an answer about an introduction over tea. None of that is a finish line. All of it is a doorway with the light on behind it. There is a practical footnote here too, in case you like your beauty with a use attached. Every time you connect to a secure website, somewhere in that handshake a computer needs to find very large prime numbers, hundreds of digits long, and it finds them by generating candidates at random and testing them. The reason that is possible in a fraction of a second, rather than being a hopeless search, is the prime number theorem. It tells the machine how densely primes are scattered at that altitude, and therefore how many candidates it should expect to try. Gauss counting chiliads by candlelight in Brunswick is the reason your bank connection completes before you have finished blinking. Nobody planned that. Nobody could have. But the practical footnote is not why anyone does this work, and I would rather leave you with the other thing. Go back to the number line, the long-ruled tape in the dark, the brass lamp lighting only the section in front of you. The primes scattered along it like farmhouses on a plain at night. Those numbers were prime before there were people. 2 is prime, and it was prime while the Earth was still molten. And it will be prime when the last star has cooled and there is nobody left to check. The distribution of primes owes nothing to human invention or human convention, and nothing even to this universe in particular. It is a fact about what quantity is, and we did not make it, and we cannot vote on it, and the whole history you have just heard is the history of a species slowly learning to listen to something that was already there. Euclid heard that they never end. Gauss heard the average, and Riemann heard the music. Montgomery and Dyson heard, faintly and by accident, that the music resembles something in the heart of an atom, and we still do not know why. There is a vertical line on a plane of imaginary numbers, and every one of 10 trillion checked points sits precisely on it, and no one on Earth can say why they should. It might be proven next year by someone currently in secondary school. It might stand for another 5 centuries. Both of those are entirely plausible statements, and the fact that they are both plausible is, I think, the most honest thing anyone can tell you about mathematics. So that is where I will leave it. The primes go on forever, thinning at exactly the rate a 15-year-old boy worked out by hand between other tasks. They wobble around his curve like a fair coin wobbles around half, and somewhere unimaginably far out they will step over it once and again, and infinitely often after that. Underneath them is a hidden ladder of frequencies that hums in the same key as a uranium nucleus, for reasons that nobody has been able to explain in 50 years of trying. That is the real shape of it, not a mystery solved in 1896. A door opened in 1859 that nobody has yet walked all the way through. Sleep well. The numbers will keep, and they have kept this long. If you want to stay in this territory, the story of infinity itself, of Cantor and the different sizes of endlessness, is waiting whenever you are.